Hi, this is Andy and thank you for joining this presentation today. We'll explore the crucial role of capacitors in FPGA design. Specifically, we'll discuss the differences between decoupling and bypass capacitors, best practices for their placement, and the importance of PCB layout for ensuring power integrity in FPGA systems. In this presentation, we'll cover the reasons for using different capacitor values and how a proper PCB design enhances FPGA performance. We'll also examine real-world examples, the Microsemi Igloo 2 for example, and highlight best practices for avoiding power plane pinching and optimizing capacitor placement under a BGA FPGA. Specifically in this example, it will be an FG484. Capacitors are essential in FPGA designs because they help maintain stable voltage levels and reduce electrical noise. When an FPGA switches states, and there can be many million of those states, it can draw sudden bursts of current that cause voltage fluctuations. Decoupling capacitors supply this transient current locally, while bypass capacitors filter out high frequency noise. Together, they ensure that the FPGA operates reliably, even during rapid switching events. Although the term decoupling and bypass are often used interchangeably, they refer to two distinct functions. Decoupling capacitors store energy to meet transient current demands, stabilizing the voltage supply. Bypass capacitors, on the other hand, provide a low impedance path to the ground reference for high frequency noise, preventing it from interfering with sensitive components. Decoupling capacitors act as local energy reservoirs, supplying transient current when an FPGA switches states. They help prevent voltage dips that could disrupt the FPGA's operation. Smaller capacitors such as 1 nanofarad to 100 nanofarad respond quickly to high frequency transients, while larger capacitors like 10 microfarad to 100 microfarad provide energy storage for lower frequency fluctuations. By combining capacitors of different values, designers can ensure a stable voltage levels across a broad frequency range. Bypass capacitors are designed to bypass noise or high frequency signals from a power supply to ground, effectively preventing it from interfering with delicate components. They act as a short circuit for high frequency noise, redirecting it to the ground, ensuring that the circuit receives an uninterrupted clean power supply. The placement of these capacitors is usually situated close to the power pins of an integrated circuit and are especially beneficial in applications aimed at noise reduction. Their main function is to mitigate high frequency noise. Essentially, they are steerage mechanisms of noise and typically consist of small capacitors such as 100 to 1 nanofarad with low equivalent series resistance to preserve high-speed signal integrity. Here is a table offering some of the key differences between decoupling and bypass capacitors. FPGA designs require a combination of capacitors with different values to maintain power integrity. The core voltage typically seen between 0.8 and 1.2 powers the FPGA's internal logic and requires rapid transient response. The I/O voltage, which ranges typically from 1.8 to 3.3, powers input-output buffers and has less stringent transient response requirements. By placing capacitors near to the FPGA power pins, designers can minimize voltage fluctuations and ensure stable operation. Using capacitors of different values helps cover a wide frequency range. Smaller capacitors respond quickly to high frequency transients, while large capacitors provide energy storage for slower changes in current demand. Placing these capacitors in parallel creates a low impedance path for transient currents, improving the FPGA's overall power integrity. This is typically shown in a PDN graph, where the graph shows an impedance over a frequency range. You would normally try and keep the PDN's impedance profile low over the frequency of interest that is deemed necessary to your system. The core voltage powers FPGA's internal logic, which operates at high frequencies and draws significant current. Let's examine this for a second. Think about an FPGA. What is it? It's got millions of transistors which are programmed in specific ways to meet a function. What is a transistor? It's a switch, but more importantly, it's a capacitor. When you switch a transistor, you are essentially either adding or removing charge in a system. Switching millions of these transistors means the cumulative effect of those transient current demands can be very large. This requires tight voltage regulation and a fast transient response from the PDM. In contrast, the I/O voltage powers the FPGA input-output buffers, which switch at lower frequencies and draw less current. While the I/O voltage can tolerate large voltage variations, the core voltage must remain stable to ensure reliable operation. A typical core voltage in a modern FPGA, as seen by this graph, is between 0.8 and 1.2 volts. The current demand depends on the logic density of the FPGA, so your core decoupling will change dependent on the device used. The switching frequency is many hundreds of megahertz to gigahertz range. It's very sensitive to voltage fluctuations, and tight regulation is needed. Whereas the I/O voltage can tolerate a much wider fluctuation in I/O voltage, but care must be taken that ground bounds and induced reflections and signal integrity issues are not created by poor decoupling. The FPGA core, what does it consist of? The core voltage is essentially powering the FPGA's logic fabric, the internal clocks, the DSP blocks and memory subsystems. As said before, it typically operates between 0.8 and 1.2 volts, draws very high current. The core logic operates at very high frequency, leading to a generation of considerable high frequency transients. Tight regulation is necessary. I/O voltage supplies power to the input-output buffers, as I previously said. It's within the range of 1.8 to 3.3 volts. Although there are I/O much lower than this now. The switching speeds tend to be slower compared to the core logic. It depends on what you are doing with your I/O. SerDes are quite fast. LVDS is reasonably fast. LVCMOS is not so fast. It can be slewed. So if you have problems with ground bounce or signal integrity issues due to not enough decoupling and your system can tolerate it, you are better to slew your design, your I/O, if you're not running very fast speeds, for instance, SPI as an example, UARTs, that sort of thing. Slow memory, it can be slewed as long as the propagation delays and the edge rates are accounted for and meet your timing demands. I/O banks accommodate larger voltage transients variations but have less stringent requirements, as I've just said, on the core. The key considerations for this section are: use multiple capacitors in parallel. Implementing a range of capacitor values helps achieve an effective performance across a broad frequency range. That's the key. Keep your PDM impedance low. Choose low ESR capacitors. It's advisable to use multi-layer ceramic capacitors, MLCC, but you might want to use LLCC, low inductance chip capacitors. It depends on your system. What is the difference? Well, an MLCC has a small pad to a large body relationship, whereas an LLCC is essentially a reverse geometry type of part. It has a large pad and a very short body, and the large pad gives a much better lower inductance presentation to the PDM. A special note is do not use X5R for applications in aerospace. They're not rated. Place the capacitors close to the FPGA power pins. Doing so reduces power rail impedance and improves the transient response. If you can, get them close to your wires underneath your BGA. Do what you can to get those chips next to the point of load where the transient current needs to be. Include several ground wires. Now, this is a bit controversial. Sometimes if you include ground wires, it can make things worse. And I'll come on to that later on. What it does do, though, it does decrease the inductance of the connection of the capacitor to the point of load, to the plane, which is what you really want, but you need to be careful doing so. In this slide, we show an example solution for a microsemi Igloo 2 part. Since the Igloo 2 have a lower power draw than SRAM based FPGAs, for instance Altera and Xilinx, their decoupling requirements are slightly less aggressive. However, a solid decoupling plan is needed for power integrity. So the microsemi Igloo 2 FPGA with its lower power flash based architecture requires fewer decoupling capacitors than SRAM based FPGAs, as previously stated. However, a well-structured decoupling plan is still essential for maintaining power integrity. For this FPGA, place 0.1 capacitors within 2 to 4 millimeters of the power pins, 1 to 4 microfarad capacitors within 5 to 8 millimeters, and bulk capacitors near the power entry points or voltage VRM modules. Now, if you can get it closer, that's better. But these are guidelines, not essentials. The guideline is try to beat what I've just said rather than not. So this is an example table of a decoupling strategy for a Igloo 2. Now everybody has a different opinion on this. It depends on the system. Engineers use the word depends a lot. It depends. Well, yeah, it does. It depends on what the FPGA is doing. Some systems require 10 nanofarad, 47 nanofarad capacitors, 100 nanofarad capacitors, all in parallel, and some 4.7s and some bulk capacitors to meet a low PDM profile. Some systems you can get away with just putting 100 nanofarad capacitors and some 10 microfarad capacitors to cut your BOM cost down and still meet an acceptable PDM. It depends on your system. You need to be familiar with the chipset you're using, and if not, then you need to use PI and SI simulation tools from Hyperlinks, ANSYS, CST, for example. That is the recommendation that I would give. PCB layout recommends it for decoupling capacitors on the Igloo 2. Okay, we've done a bit of this already, but I'll just go through the slide. So 100 nanofarad caps between 2 and 4 millimeters, 1 microfarad to 4.7s, 5 to 8, bulk caps around the periphery. Distribute the capacitors around the FPGA. Do not cluster them up in one side. Okay, there are plots showing that you can push all your decoupling capacitors up one edge of the board and still meet a low PDN, right? And the graph might show that. But in truth, what happens is, depending on the system and depending on the current demand at that time, you are pulling current across the board. It's not always a certainty that your interplane board capacitance will suffice. And what do I mean by that? Sometimes we use a ground plane or a reference plane next to a power plane to create a very tight capacitive couple that is used to support the high frequency transients from modern FPGAs. That system is not a guarantee, it's a guidance, it's a best practice. So the best practice would be, if you can, is to distribute your capacitors around the point of load of interest. Use the shortest possible traces where possible. To a multiplexer, analog multiplexer input, you want to keep the local charge transfer very close. Okay. Select low ESR MLCCs or LLCCs, as I previously mentioned. Use X7Rs, that's superior than the X5Rs. They're not rated for aerospace. Strive to minimize inductance, and that's where your LLCC parts come from. If you can't use planes, use thick traces or wide polygons for power connections. Don't use skinny little tracks, they're inductors. Always maintain a solid ground plane. I don't like the word ground, even though I've got it here. I like reference plane. Beneath the FPGA to ensure low impedance return paths. I should change that slide. Implement split player planes for different voltage domains, VCC, the VCCIO, the PLL filters and so forth. You can get away without a PLL plane if you can get your capacitors right next to the point of interest and then your ferrite bead connects to a power plane. I'll show that later on. The core voltage in an Igloo 2, the VCC 1.2, use a compact configuration of 0.1 microfarads, typically, can be different values, around the FPGA, next to the power pins. Ensure that the wires connect directly to the solid ground plane to prevent lengthy traces. Okay. It's crucial to remember that low inductance power delivery is vital for rapid logic switching. The rapid logic switching, it's trying to suck the current as fast as it can into its own local PDN to maintain that voltage level. Consider the sensitivity to noise in clock circuits requires low noise power supplies, which gets us onto ferrite beads. Ferrite beads can be an advantage and they can be a disadvantage. Going left to right in your mind's eye, imagine you've got a power supply and then a ferrite bead and then the power supply which the ferrite bead is supplying. Okay. A ferrite bead is essentially an impedance. It's a filter. So if the right hand side of that bead wants current very, very fast, ferrite beads can be detrimental. Yes, it's stopping that high frequency transient noise from propagating to the left onto the general power plane that's feeding that bead itself. So what do you do about that? Well, on the right hand side of the ferrite bead, the one that's connected to the noisy signal, make sure you've got ample decoupling capacitors. That way your ferrite bead is filtering noise, so it's localizing the noise to that small area on the right, but the decoupling capacitors are feeding that high frequency transient with current. Okay, it's not going to pull it through the bead, it's going to pull it through the capacitors. Okay, so if you don't effectively decouple on the right hand side of a ferrite bead, you are being detrimental to your PDN for that point of load. Okay. Refrain from crossing power domains close to these lanes. It causes noise. Conduct an IR drop analysis to verify reliable power distribution and use decoupling capacitors to optimization tools. For instance, the ANSYS, the Hyperlinks, CST. Those are all power integrity and SI signal integrity tools. If you've got the availability to use them, I suggest you use them. it is also a good way of closing the loop from the hardware to the simulation point, so you can actually start to trust the tools. Measure the power rails noise with high bandwidth probes, clip springs. Don't use the little 6-inch earth probes, they're no good. Pull them off your scope probes. You know, very, very, very close measurements with the tip of the probe and a ground coupled measurement. You can get special pins for your scope probes. High scope probe bandwidths, low impedance, low capacitance. Make sure you can actually read the frequency of interest that you're trying to read. Don't forget another thing that people think of, which is a different thing to this, is but people go, oh well, I've got a 1 gig scope and I've got a 1 gigahertz probe, but you haven't got a 1 gig system, because it's a combination of the 1 gig scope probe and the 1 gig scope. You've got much less than that. So if you're looking for 1 gigahertz frequency signals, you know, you need, you know, your 3.5, 4 gig probes and your 10 gig scopes, just so you can really look at those signals. Okay. And evaluate the transient response by adjusting the FPGA loads. So if you can, look for massive toggle events on your IOs. Try and get some pat code in there to look at the toggling events of your IOs, of constantly switching, and see if that your decoupling can meet worst case power switching from your IO. Put extra code in, put PATS code in, and switch all the logic elements in your FPGA. Typically when you're doing an FPGA design, you only use about 50% of it. Well, what happens in years to come when the customer says, I want this extra function, and then you try and put that in, the system starts to fall over. Well, you need to fill the FPGA up and run it not at the frequency that you're currently running at, but higher frequency, and make sure that you are still having a performance that's acceptable in your system, that the FPGA is not falling over, that the noise floor is acceptable, that there's no voltage dropping, there's no excessive ripple. So it's not just about writing a bit of code, throwing it in, kicking it out the door, because the customer might want something different later on. So just think about that when you're doing your designs. Okay, vias, power pinching, importance in power planes. Okay. Proper via design is essential for maintaining power integrity, especially in BGA FPGAs. Why is that? Well, if you're using 3-hole vias, you're going to put a lot of holes in a small area, put it that way. Incorrect via clearances can lead to power plane pinching, where closely spaced vias reduce the effective copper area of the power plane, depending on your power plane clearance rules. This increases resistance and inductance, impairing power delivery and causing voltage drops. Okay, let's investigate this a little bit more. Okay, effects of power plane pinching. Okay, so you get an elevated power supply impedance because you're cutting copper out your planes. An impedance means a voltage drop. So if you've got a higher voltage drop, a higher demand is going to cause a higher voltage drop. It's an impedance, so they're proportional. The other thing to think about is if you're cutting copper out from underneath a part that may get hot, then you could raise the temperature of that part, and that might be a consideration for you. Not all designs can lump a bit of metal or a peltier on top of a chip and cool it down. Most aerospace designs build their thermal impedance and cold walling into the PCB itself. For example, if you designed a board that was on an aircraft that landed on an aircraft carrier, you wouldn't want a big lump of metal hanging on a BGA. When it hit the aircraft carrier deck at 40G, it would just probably snap off. Okay, so we tend to not do that. We tend to design an impedance into a thermal impedance. I'm not talking about electrical impedance now. A thermal impedance such that it draws the heat away from sensitive parts that get hot. But if you get your via power plane clearances wrong, you essentially start to remove all that copper, and then you haven't got the low thermal impedance that you think you have. Okay. Here's an example what I'm talking about. Here's a picture of a bad set of clearances for a 484 BGA. It's got a 1mm pitch. This is an Igloo 2 example I've set up. The wires in blue that I've circled are ground wires. They are connected directly to the plane. Okay. The wires circled in red are also ground wires. Because the wires around it are I/O wires, or wires that are not connected to that ground plane. They have a power plane clearance, and essentially it has removed the copper. So there's nothing connected to those little nunchucker wires, as you want to look at them. They're just floating. They're useless. Okay. How do we do this? Well, this is what you do. You alter your power plane clearance rules, and now those same wires that we saw in the previous slot, there you go, same wires are now connected to a solid ground plane. Okay, you've still got perfect good clearances, everything's good, right? So you need to address power plane clearance rules. They not only affect your chip from a thermal point of view, but they just create impedances in your planes, which is not good. Okay, so best practices to avoid power plane pinching. I'm not going to go through this. All I'm going to say is remember power plane integrity means high inductive, high impedance PDN, and that results in poor performance. The other thing I would say is it doesn't matter how much decoupling you throw at an FPGA or a chip. If whatever the decoupling is connected to is degraded from an impedance point of view, like in power plane pinching, it's going to have a degradation effect on your PDN. Doesn't matter how much decoupling you put in. Okay. Here's an example of a -25. The -25 Igloo 2 is a very small FPGA. Okay. In this instance, this chip was only running around 40 megahertz, so it's not running exactly fast. Okay. So what have we got here? We've got some core decoupling. There we've got some extra bigger decoupling ones. In those instances, those are 10 mics. So I've got some 10 mics, got some 100 nanofarad caps there. The PLL filter doesn't need to be on a plane, it's connected right next to it, and the I/O decoupling is spread around. Okay, so when you look at fanning out a BGA, an FPGA in this instance, if you fan it out in a quadrant style, you will notice something quite clear. And that is a big cross in the middle of the FPGA. It goes from top to bottom, left to right, and there's no wires in that area. And that is where you can put your decoupling. Yeah. The other thing to think about is if your BGA, your FPGA, is only servicing a 3.3 volt system, in case of an Igloo 2, the MSIOD pins, which are only 2.5 volt tolerant or lower, won't be used. As such, all those I/O won't have wires connected to them, so you'll have area to place extra decoupling. Maybe even, if you're clever enough, to put your 1.2 core volt power supply there, and actually get an extremely close coupling of your core voltage, VRM, and decoupling capacitors. So you need to play around with these things. Okay. Here's that same example where we've got on the left hand side is the chip itself, the clock and JTAG, and underneath the board there's the decoupling. Okay. Package sizes. Now, placing decoupling capacitors directly beneath the BGA FPGA can be challenging, but it will improve the transient response by minimizing the distance between the capacitor and the point of load, requiring that current injection, that charge injection. Typically in aerospace we use 402s as a minimum. On our sites, commercial 0201s, you'll easily get an 0402 and a 1mm pitch BGA. There's no issues. So here is a bit of a table that you can use. Typically 0402s would be the 1, 10s, 47 nans, 22 nans, 100 nans. Maybe you get up to a microfarad, depending on the voltage rating and your derating standards that you're using. After that, the 0603s and the 0805s come into their own, where you can fit them still under the device, as shown here. Yeah. And that would aid in your PDM because you're bringing them close to the point of load, but you can move them slightly further away. Okay. Again, like I've just said, 0201s, 402s, right underneath the pins. You can use the 0603s or 0805s just outside the BGA field. If you can get them inside, that's better. And the higher level bulks, the 10 microfarad, 22 mics, 100 microfarads, they can go on the periphery of the FPGA. It depends on your inspection techniques, whether you use an ursoscope or you just x-raying as how close you can get your capacitors to the BGA on top layer, the same layer as the part itself. Most people these days they x-ray things, so you can get it close, especially with IR reflow technologies and so forth. You can compact things quite a lot. So and then you get your VRM, your point of load. Just if you've got a 1.2 core voltage and it's only servicing the FPGA, don't stick that power supply on the other side of the board, as I've seen so many people do. Stick it next to the point of load. All right. Okay. This is just an extension of what I've just said. Don't use X5R capacitors. You can use wiring pad for enhanced decoupling technologies and so forth. It really depends on the cost break of your system, whether you're using blind and buried or so forth. If you're using blind and buried technology, you'll find that you'll have far more space underneath your BGA on the backside for all your decoupling. You'll probably fit a power supply underneath there. To be honest, I have done in the past many times. If you're using a through-hole part, for instance, on an aerospace 2.4mm PCB thickness, we would use a typical 0.3, 0.6mm hole annulus via, or in freedom units, it'd be a 2412 via. I'm talking thous now. But even so, you should still be able to meet all the decoupling placement requirements on that type of card. It only gets more challenging when your pitch size goes down. And if the pitch size goes down, then the capacitor, the FPGA part size goes down. So you might have to use blind and buried at that point, and so forth. So you will get your capacitors underneath. So the technologies tend to support themselves, and the more aggressive parts, especially CPUs these days, they've got on board capacitance, on die capacitance, to help alleviate that challenge for the PCB designer. Now, an additional topic while we're at it is I teardrop all my boards. It has a few advantages. One, it creates a better mechanical bond from bio to pad. It lowers the inductance for another, which is good. And I don't just teardrop my vias, which some people do. I actually teardrop my component pads as well, as seen here. So if I have an IC, for instance a SOIC, the track coming out the middle of the pad of the SOIC would have a teardrop effect. And I find I get far more reliable PCBs doing it that way. And it survives far more far higher mechanical stresses from what I've witnessed as well. And I've added more copper. It doesn't really impact signal integrity at all, to be honest. And that's super high frequency, right? Of which you'd be using microvias as well with micro teardrops, so it all scales as well. So that's what I do. So the key takeaway is consider connections to the teardrop components, not just the vias. Okay. So this is the end of this presentation. So in conclusion, selecting and placing the right capacitors is essential for maintaining power integrity, ensuring reliable FPGA operation. Decoupling capacitors provide transient current to prevent voltage fluctuations, while bypass capacitors filter high frequency noise to maintain clear power lines. That's it for this presentation. I hope it's added some value and given some brief insight to what FPGA requires in terms of capacitors for them to function correctly. Thanks for taking the time to watch this presentation. Hopefully do all the usual stuff on YouTube. That's comment, subscribe and share the presentation. Do what you want with it. Cheers. This is Andy, and as usual, have fun with your electronics.